so fluffy and light. I can't believe these are from chickens.
It's for birds, and we are leveraging especially the insulation properties of feathers for our product.
So you have a company that takes chicken feathers and turns it into a really useful material.
Initially, if they come from the slaughterhouse, they will be heavily contaminated. So they will be full of blood, feces, water. They're very moist as well, so it's really a horrible material, to be honest. So it's not a nice matter to deal with. So initially there is a washing process. So we clean the feathers actually to a bedding standard. They're so clean you could sleep on them. Here's an example. This is basically the world's first textile made from chicken feathers, and it actually outperforms polystyrene by 5 hours.
So that white kind of foamy board that we get in packaging could be replaced by this.
That is correct, yeah. What we're using it for is for food delivery packaging. If you would, for example, order a food delivery box with fresh ingredients, it will get shipped to your house, and what couriers often do, they just drop it at your doorstep. And especially in the summer, that's a big problem because there's food spoilage, especially in temperatures that are quite high. It's fully biodegradable, actually.
The problem with CO2 is that it's a very stable molecule. So in the first step, we activate it. So we turn CO2 into a very active molecule, and with this molecule we can do with a very interesting chemistry. So we've got a two-step process to produce the building block of polyester. We are turning CO2 into new virgin fibers.
That is a sandwich that is going to convert carbon dioxide into carbon monoxide, stage 1 of the process.
So we'll implement now this cell into my catalytic bench.
So it's bubbling away, you're collecting carbon monoxide, and what happens next?
Next, this carbon monoxide, after collecting, will be used in the stage 2.
So apparently you're stage 2.
Yes, I'm stage 2 and 3.
2 and 3?
Yeah.
Okay. And what happens in stage 2 and 3?
So basically I'm taking what Dr. Gosh does. So it's making a gas molecule called carbon monoxide. And I will mix this molecule with a liquid. And this mixture liquid gas will obtain a molecule. And this molecule is the molecule for the stage 3.
Ah, okay. So you're basically mixing one chemical with another, and then that chemical with another chemical to get the liquid that you need, which is the major ingredient of polyester.
Yeah, exactly.
Polyester is huge. We don't realize it, but 60% of the cloth we buy today are made from polyester. And today, so polyester is a plastic made out of petroleum. And with our solution, we are replacing the petroleum product with CO2. We take this liquid and we mix it with a solid to produce polyester. So polyester is a polymer. That means that it's a repetition of building bricks. A, B, A, B, A, B. So we produce today the brick A and we mix it with a brick B that is used in the industry today to produce polyester pellets. So it's a small chunk of plastic that are used to produce textile.
The moment we've arrived at the result. Wow, so from a gas to this.
So our main goal is to decrease the carbon footprint of the textile industry. It's huge, and with the technology today, we can reduce the carbon footprint by 70%.
Just got to RS Group, where I'm going to be meeting Navjot Sawhney. He started the washing machine project.
He's created a manual drive washing machine inspired by the stories of families in refugee camps.
A washing machine that doesn't use electricity, which means it's going to be filled with loads of really clever engineering.
I moved to South India to make clean and efficient cook stoves. There I met my next door neighbour, Divya, and Divya's life was an everyday struggle, whether it was foraging for wood or hand washing her family's clothes. You can see
I'm particularly fond of the lid. It's like where all the engineering lies.
This is where all the technology is.
Gosh, this is like you know, power steering.
Yeah, exactly. We're standing around a table and we saw a salad spinner in the corner. So it's geared here.
Oh yeah.
Can you see the gears there?
Yeah.
So it's pretty easy to take apart as well. So that is how simple it is. This gear slots into that gear here, essentially. So one turn, and this turns multiple times. Minimum effort, maximum spin.
Yeah, one revolution means this spins 20 times faster. You're literally working with angles and gravity.
Exactly. This is gravitational draining, like the salad spinner.
We're doing the same thing.
Same thing.
Whichever way you look at it, driving petrol-driven cars puts a huge amount of carbon dioxide into the atmosphere, But what if you took that carbon dioxide and turned it from a problem into a solution?
In our case, we are looking at technologies that can capture CO2 from anywhere. We're not looking at a specific source of CO2, we're just looking at CO2 that is already present in the atmosphere and targeting those very dilute concentration, but still very important for the planet. We're using what's called an adsorbent. So basically, an adsorbent is like a sponge. It works more like a Brita filter.
So are you saying that the technology may help to mitigate carbon dioxide in our atmosphere is actually in our kitchen? Absorbing CO2 already in the atmosphere is one thing, but factories and power stations continue to burn fossil fuels. Dr. Colin Hale is working on an ingenious way of catching that CO2 before it escapes into the atmosphere, and how this could result in even greener transportation.
So this is a pilot scale carbon capture facility. It's replicating the sorts of process that you would use for example, removing carbon dioxide from the flue gases coming out of the chimney of a coal or a gas-fired power station. It's about capturing the carbon dioxide before it goes into the atmosphere.
I don't know if you can see this clearly, but what I'm looking at is rain inside a pipe, essentially. And it's where liquid meets CO2 gas, and the reaction that happens between them is really where the CO2 is captured. And why this is so essential is because this is the first step in making sustainable vehicle fuel. Is the synthetic fuel that you are developing actually performing as well as petrol?
Yes. In fact, what we do is we check the chemistry first of all. So we check what we've made by doing a lot of detailed chemical analysis, and we can see it's as good as existing fuel. In fact, we would say it's better because it doesn't have impurities in it.
It's quite fascinating to think that motorsports, for example, could be leading the way, encouraging the development of this technology. What I love about what I've seen today is we acknowledge that we've been creating a problem. We've been burning fossil fuels, releasing CO2 into the atmosphere. But what I saw today here at Imperial really shows that we're taking the problem and we're turning it into a solution. And that's really where engineers can make such a massive difference.